If you were to ask me for what classical systems are Hamilton's equations valid, I would tell you for those systems that are deterministic and reversible, that conserve entropy, either thermodynamic or information entropy, and for those that conserve uncertainty. And why am I so confident in saying that? Well, because I reverse engineered the equation to have a precise sense on what they say mathematically, geometrically, and physically. And this is what I want to share in this video. We're going to take Hamilton's equation for 1 degree of freedom and find 12 equivalent characterizations. That is, 12 conditions from which we can rederive Hamilton's equations. 8 conditions are going to be on the math and the geometry. 4 are going to be on the physics. So if you get lost in math, don't give up, just skip ahead to the physics. But really, seriously, you should really look at the math and make sure that everything I say makes sense. You shouldn't trust me, you should trust the math. And once we have gone through the whole single degree of freedom, then we are ready to look at the general case, multiple degrees of freedom, but not in this video. We're going to do that in another video. So let's start with 12 equivalent characterizations of Hamiltonian mechanics for a single degree of freedom. So here are Hamilton's equation. dq dt equals partial h partial p, and dp dt equals minus partial h partial q, where q and p are position and momentum, and h is the Hamiltonian. I'm going to use a slightly more compact notation. Instead of having d dt, I'm just going to write dt. It's going to make the notation a lot more streamlined. And then for the partial derivative, I'll just write partial p. And what I want you to think about this equation, I want you to think as this derivative as a vector field. It's something that for each point tells you how the states are going to move in phase space. And then we have a relationship between this vector field and the Hamiltonian, the partial derivative of the Hamiltonian. So the first thing that we want to understand is exactly what is this flow, this displacement field, what are its characteristics, and how we can think about it in terms of the Hamiltonian. So the first goal is to understand how states flow in Hamiltonian mechanics. Okay, so we start with a Hamiltonian. For example, this is the Hamiltonian for a harmonic oscillator. And the bluer it is, the higher the value of the Hamiltonian. And these lines here are surfaces at equal h. So this would be h equal 1, this h equal 2, h equal 3, and equal 4 in some units. They would form circles, right? So this is the Hamiltonian. And so it's just a function of position and momentum. Then from the Hamiltonian, we can take a gradient. So the gradient is going to be partial q in the direction of q and partial p in the direction of p. And here we can see what the gradient does. It's going to be perpendicular at the surfaces at constant h. And we will point where the h is increasing, and the faster it is increasing, then the greater the gradients. Okay, so this is the gradient of the Hamiltonian, and you see that it's kind of related to Hamilton's equation because we have these partial q and partial p, but in Hamilton's equations those are in somewhat different order, right? The p goes inside the q part, and the q part becomes the minus p part. And what happens geometrically is that switching the order and putting a minus sign is essentially a rotation by 90 degrees. So if we go to the previous slides, this is the gradient, and then we go to the next slide, we see that the gradient rotates 90 degrees. And now this gradient rotated 90 degrees is exactly the flow of state. So the flow of state, the displacement field, is just the gradient of the Hamiltonian rotated 90 degrees. And you can see here already right away why the Hamiltonian, the value of the Hamiltonian is conserved during evolution. Because if the gradient is perpendicular to the surfaces as constant h, if we rotate it 90 degrees, then it's going to be tangent to the surfaces at constant h. So whenever we move, the flow is going to be on surfaces at constant h. So you can already see very geometrically, very easily, a fundamental property of Hamiltonian system. Okay, so let's turn these things out in actual math. we can write this omega, which is a matrix 0, 1, minus 1, 0, and this is a 90-degree rotation. So if we take the gradient and multiply by omega, what you see is that we do the switcheroo and take the minus sign, and this is going to be equal to the displacement field. A better way to write this, better because it generalizes better to multiple degrees of freedom, is to write our omega in component form with A, B being the indexes. So if you studied relativity, this is exactly the index notation that you use there. It's very useful and very powerful, and we're going to use it here. And so what you have is that this SB is the displacement field, where B spans Q and P, the different component. And then we contracted with this matrix here, with the first, the B here with the first index of omega. And you can think this as a lower a as the rotated field. And this is what it's going to be equal to the gradient of H. And if you go and substitute the actual possible variable here, you are able to go and rederive Hamilton's equation, because now this omega qp, it's this element, so this is 1, so you have SQ equals partial PH, and if you get PQ, this would be this element, which is a minus 1, so you would have minus SP equals partial Q of H. Okay, so this is sort of a rewriting of the equation. We have a little bit more of a geometrical sense of what's going on. We basically have seen that the gradient of the Hamiltonian is equal to the displacement field rotated 90 degrees. Okay, that's very good. And this HMG stands for Hamiltonian mechanics generalized version, because, as I said, this exactly this form will actually generalize to multiple degrees of freedom, just where the omega is a little bit more complicated. And as I said, we'll see that in another video. Okay, so this is already an interesting thing. But again, this idea of switching and putting minus sign might make you think about something else. So for example, if I have a vector and I calculate the curl, you see here that there is again something like switching order of things and putting minus sign. In fact, if you had a field, a vector field that is component 0, 0, and h, you would see that you would have a derivative in terms of y of h minus a derivative in terms of x of h. So you're kind of doing something here. There is some similarity between what we have here and what we have here, right? So it's some kind of vector calculus type thing that we are doing. And if you studied your vector calculus, you know that the divergence of a curl is 0. And so let's go and calculate the divergence of the displacement field. That is, we are going to take the sum of the derivative in Q with respect to Q plus the derivative of P with respect to P, right? We derive and sum all the components. And if we use a Hamiltonian equation, we know that SQ is equal to partial PH and SP is going to be minus partial QH. And now you see that these are just the mixed derivative taken into two different order, and these are equal to each other, and therefore this is 0. And so if we get the Hamilton's equation for 1 degree of freedom, then we have the displacement field, the flow is divergenceless. And what does that mean geometrically? Well, if you have a flow of states that is have divergence equal to 0, the flow of states is incompressible. That is, if you take a region of phase space and you look how the states flow inside the region, you will see that as many states flow in, as many states flow out, right? No state remains inside. And this is what we say, that the flow of the states is incompressible. And now we could ask the opposite question. Suppose that we start with a flow, a displacement field that is divergenceless. Can we get back Hamilton's equation? And it turns out that we can. So if we have now 2 points, 0 and P, right, and we take this closed region, right, we know that the flow through this closed region is going to be 0. meaning that as the flow over this part is going to be equal to the flow over this part. And so the flow through OP is path independent. No matter what path we choose between O and P, the flow through that surface has to be equal to all the other surfaces. And so what we can do is pick a point, this O, and set a function there, our function h to 0. And then we can say that h at P is just the flow of the displacement field through the surface that connects 0 and P. And again, surfaces in a two-dimensional space are lines. So basically it's the flow through the line. And so we have that h of P is just equal the integral of SQ dP minus SP dq, because we're essentially taking some sort of cross product between the flow and the line element of our curve here. And now, if we have defined this to be h, right, then the differential of h is just equal to partial QH dq plus partial PH dP. But look at here, this is the h as well. Therefore, we have to have that this part here, minus SP dq, has to be equal to partial QH. And this part here, SQ dP, has to be equal to partial PH. Therefore, this is equal to this, and this term is equal to this, and these are exactly Hamilton's equation. So a divergence field admits a potential H, right? And the potential is actually the Hamiltonian. And the more proper term is not really a potential, it's called a stream function, but it's basically a potential. It's just that you're doing something slightly different than what you're doing with the scalar potential, which is usually for gradients and not gradients curl and not curls and divergence. So, okay, so we've found that the Hamilton's equation for one degree of freedom are equivalent to saying that the displacement field is divergenceless. And again, this is another way that we can think of Hamilton's equation, which is a lot more geometrical than what we have seen before. Okay, now that we have looked at how the displacement and the flow of states work, let's look at the Jacobian transformation and how volumes and density transform in Hamiltonian mechanics. So, first of all, let's recall what's the rule for the transformation for an infinitesimal volume. So if we have a coordinate, we're going to use xc for coordinates that span the whole space. So we have a set of coordinate xc, and we make a transformation xc hat. This is going to be the new coordinate in terms of the old coordinates. And then we can create, we can look at how the differentials are transformed. And we're going to find that the new differentials are going to be, the differential of the new coordinates are going to be the Jacobian matrix multiplied by the differentials of the old coordinate. And this is true for a generic manifold, for any state that can be charted with quantities. And what we're going to look at is how the volume, the product of all the differentials transform. And what happens is that the product of all the differentials is the Jacobian determinant multiplied by the volume on the old coordinate. In our specific case, for position and momentum, we are going to have the old position and momentum, and this variable gets moved around in phase space, and this is going to be our Q and P, the new values as transported by phase space. And we're going to have a Jacobian matrix, a Jacobian determinant, that is going to be the derivatives of the new coordinates with respect to the old coordinates. If we make an infinitesimal time step, then the momentum is going to be the old momentum time plus the displacement field along momentum times the infinitesimal displacement, and the same thing for the position. So if we now work out our Jacobian matrix, when we go and derive things, we are going to have an identity matrix here, 1, 1, and 0, 0 for Q equals to Q and P equals to P. And then we're going to have these terms that are going to be derived, that are going to be the partial derivative with respect to Q and P and Q and P. Okay? So this is our Jacobian matrix, and we want to calculate the determinant, which is going to be this term times this term minus this term and this term. And so we just write it here. And we're only interested in the first two, the leading order, which the first one is 1 and 1 multiplied by 1. So it's 1 because those are the only term without a dt. And the terms that have a single dt are going to be this term multiplied by this term and this term multiplied by this term. So we have partial q as q plus partial p as p. And lo and behold, this is just the divergence. This is exactly the divergence. So the leading term to a first approximation of the Jacobian determinant is actually the divergence. And so now, if we want this, since we know that this divergence is equal to 0, this is exactly the same condition from when the Jacobian is equal to 1. So if the Jacobian determinant is 1, then the divergence of the displacement is 0, and if the divergence of the displacement is 0, the Jacobian determinant is 1. These are exactly two equivalent conditions. But we saw before that the divergence being equal to 0 was a characterization that it's equivalent to Hamiltonian mechanics. Therefore, now we find that the fact that the Jacobian of the time of evolution is unitary, the Jacobian determinant is 1, is exactly an equivalent characterization of Hamiltonian mechanics. Now, as we saw before, the Jacobian tells you how the infinitesimal volume elements transform. But of course, if the infinitesimal volume element are always the same than when they are transported by Hamiltonian mechanics, then it means that the full volume is also conserved. That is, if we start with a region in phase space, the transported region, the way that the flow works is that the final region will have the same volume of the initial region. And again, this is exactly saying that the Jacobian determinant is 1 everywhere. Therefore, the fact that volumes are conserved through the evolution is an equivalent characterization for the Hamiltonian mechanics in a single degree of freedom. Well, something else that transforms like the volume is densities, because densities are a quantity over a volume. Right? So if we have a probability density, well, the volume is going to transform in one way, the density is going to transform in exactly the opposite way, because a density is 1 over a volume. So the new density multiplied by the Jacobian determinant is equal to the old density. But again, these two are going to be equal if and only if the Jacobian determinant is 1 everywhere. So this is again yet another equivalent characterization of Hamiltonian mechanics, the fact that densities are conserved through the evolution. And what does that mean? Well, suppose that this is a probability distribution and you apply Hamiltonian mechanics, therefore this probability distribution will move around. But the way that it moves around is that the value here is going to be exactly the same value at the final point. So the probability that you have to be in the initial state is exactly the same probability of being in the final state, right? So there is this, the thing is mapped one to one. It can't stretch, it can't compress, right? It's always sort of the same distribution that moves. Of course, it can sort of fold in a very complicated way, but still the value of the density is mapped exactly from the initial point to the final point. Okay, so these were characterization in terms of Jacobian densities and volumes. Now we have another set of characterization that are a little bit more complicated, but actually these are the characterization that turns out to be more important because they generalize. And so we are going to look again at this omega, which was this matrix that we thought before as rotation. We are going to look at Poisson brackets. If you have studied Hamiltonian mechanics, hopefully you know what these are. And then we're going to look at the curl of the rotated displacement. Instead of the divergence of the displacement, we're going to look at the curl of the rotated displacement. So let's go and see it. So if we have two vectors, let's say this v and this vw, and we want to calculate the area, what we're going to do is simply multiply the q component of v times the p component of w minus the p component of v times the q component of w. So this is the expression to compute the area, and this should remind you, of course, of the cross product. But another way that we can express this is through the matrix omega. Because if we make this, if we take these two vectors and sort of multiply it on each side by that matrix, it turns out where we're going to have exactly this expression. Because if you remember, QP was a term that was non-zero and it was 1, and PQ was the other non-zero term and that was -1. So if we do all the multiplication, you have 0 terms and these are the only 0 terms. So this is another way to compute the area given two vectors. And now imagine that we have, again, something that transports these vectors around. And the transformation rule for vectors is just to take these vectors and multiply them by the Jacobian. So these are the new vectors, where they end up in the final time step, and as a function of the initial one. So you can take now, you can calculate the area of the new the transported vectors, and again, as is going to be like this, we just take the two vectors and multiply them with our matrix, with this element by element multiplication. And then, of course, we can re-express these vectors in terms of the original vectors and these Jacobians. And then what you can see is that this omega hat, it's basically becomes this matrix over here. These are just products of matrix. So you have a matrix inside here sandwiched in between V and Q. And now what happens is that this matrix is basically going to tell you the area of the transported vector, right? So this is basically the future area if you started with V and W, right? This is the initial area given V and W, and this is the future area given V and W. But if areas are conserved, if volumes are conserved, then these two values have to be the same, and therefore these matrices here have to be the same. And so requiring that the volume is conserved is exactly requiring that this matrix omega AB remains invariant during the evolution. And this matrix omega AB in mathematics plays the role of essentially what the metric tensor does in general relativity. If you studied that, you know that there's a metric tensor that basically defines the inner product, the scalar product between two vectors. And this omega is basically doing something similar. Is essentially defining some geometrical aspect, but the geometrical aspect that is defining are not the distances and the angles, but it's these areas in phase space. So really the geometry of phase space is the characterization of these areas, and therefore the fact of this symplectic form, that the geometry is preserved by the evolution, is exactly requiring that we have Hamiltonian mechanics. This is a more sort of geometrical representation that mathematicians would like to think about. So this is exactly what this means. Okay, so this is yet another equivalent conditions for Hamilton's equation. And we can sort of understand now what happens if we have two vectors and they start and they have a particular areas. Well, these vectors can rotate, the angles between them can change, and the length can also change. as long as the area remains the same. So if you imagine two little vectors moving around, they can do all these sort of motions, they can do many things except that they can't change the area, they can't change the volume, so they can't both become bigger and keep the same angle. And they can't change orientation, they can't flip around, because that would have a negative Jacobian, and the Jacobian has to be positive in a continuous transformation. Okay, so this gives us a sense of what's happening. And now we can find yet another characterization. Suppose, for example, that we are transforming volumes from Q and P to two other variables that are F and Q. And F and Q you can imagine as like two general quantities, right? And again, you would have a Jacobian matrix between F and G and Q and P. And you will be able to calculate the Jacobian determinant, which is going to be partial F partial Q, partial G partial P, minus partial F partial P, and partial G partial Q. And if you've recognized this expression, if you studied Hamiltonian mechanics, this is the Poisson brackets. So the Poisson bracket is actually a determinant, and so again it makes sense, since we saw that determinants are, the Jacobian determinants are a way to characterize Hamiltonian mechanics. It makes sense that these Jacobians, the Poisson bracket, have an important role. Another way that we can express this is in terms of omega upper AB, and omega upper AB is essentially the inverse of omega AB, such that if you multiply them like this, you would get an identity matrix. And it's basically like omega, it's just that you have a minus sign in front of it, essentially. And so you can write this again in terms of omega AB in this way. And now that you've written in this way, you know that omega is conserved by the evolution. Well, if omega is conserved by the evolution, the inverse of omega is also preserved by the evolution. And therefore, the Poisson bracket calculated in the new coordinates, in the new P and Q, has to be the same as the Poisson brackets calculated on the old Q's and P. And so the fact that the evolution leaves the Poisson bracket invariant is yet another characterization of Hamiltonian mechanics, because this is equivalent to the characterization with the symplectic form. Yet another way that we can look at this, we saw before that we could characterize Hamiltonian mechanics as having the flow of S through a closed surface be zero all the time. And we saw before that this cross product can be expressed in terms of the omega, right? So this SQ dP minus SP dQ is actually the same as multiplying this and this with the omega in the middle, because it exactly does that. It changes the order and puts a minus sign. But now remember that this omega here, we can also see it as the 90-degree rotation. So if we apply this 90-degree rotation to S, we get the S lower b, and this is the rotated displacement field. And now this, we have the same expression here, but now here we have a dot product. We don't have a cross product. So now this is the flow along the curve. So we started with the flow of the displacement through the curve, and now we have the flow of the rotating displacement along the curve. And this is going to be zero. But if the flow of the rotated displacement along closed curves is zero, then this is exactly the same as saying that the rotated displacement field is curl-free. And so this is yet another characterization of Hamiltonian mechanics. So, as you see, there are a lot of characterizations that we've done. We've found 8 different mathematical characterizations, and you could go, see them, absorb them a little bit more slowly, and you could get a little bit, with few examples, a little bit more of understanding of the geometry of what's happening, both mathematically and geometrically. But of course, we are interested in the physics. So what are all these characterizations telling us about the physics of what actually is going on in terms of physical systems? So first of all, note that Hamiltonian mechanics is about transporting areas and densities, not just points. Because this is what differential equations do. They talk about Jacobians, they talk about areas. We saw those things were important. So classical point particles are really better conceived as infinitesimal regions of phase space, right? Thinking that they're really points sort of breaks that whole structure and breaks all these equivalent characterizations, because really Hamiltonian mechanics is transporting areas, infinitesimal regions of phase space. And objects then are really considered point-like when their size is negligible compared to the scale of the problem, but the size is there, is never zero. It's something that we are, not considering anymore, but it's something that is always there. And this actually matches in what we actually, and how we use classical mechanics when we do fluid dynamics and continuous mechanics. We always think of the infinitesimal pieces and the forces acting on those infinitesimal pieces and so on. So this actually makes the whole thing on classical mechanics more coherent. Another thing to note is that in statistical mechanics, we use volumes of phase space to count states. For example, in this textbook, we define the microstate count as the dimensional quantity, the dimensionless, the labeled volume in phase space. You see we have an integral in d lambda here, which really represents phase space. So we already have a physical connection between phase space volumes and physics. And so Hamiltonian mechanics, we saw, preserves volumes, which means that the final region has the same number of states as the initial region. So if we imagine that all these states are being in sort of infinitesimal cells of phase space, we're mapping these points to points, and we're mapping these regions to regions, and these regions have the same number of states in the beginning and the end. This means that for each initial state, there is one and only one final state. We are making the initial and the final state in correspondence as a one-to-one in the count. Therefore, this tells us that the preservation of volume actually is equivalent physically to an evolution that is deterministic and reversible, in the sense that states are mapped one-to-one. For each initial state, there is one and only one final state. And so, now, this sort of presents a puzzle, right? Because why should deterministic and reversible evolution give us Hamiltonian mechanics? What is the connection between determinism and reversibility and conservation of energy? Well, you can think it like this. We have a system and an environment, and the system is evolving deterministically and reversibly, which means that the past and future of the system depends only on the state of the system. Which means that the past and future evolution does not depend on anything else. In particular, it does not depend on the environment. The environment can do whatever it wants, is not going to be affecting the system. So in this sense, the system is isolated. Its evolution does not depend on the environment. And then we know from the first law of thermodynamics that a system that is isolated conserves energy. So essentially what we have found by going from determinism and reversibility to Hamiltonian mechanics, it's kind of a stronger version of the first law of thermodynamics, in the sense that not only we're showing that a system that is deterministic and reversible, which means that it's isolated, has to conserve energy, but an energy exists, a Hamiltonian exists, and the Hamiltonian is really the potential for this flow of states that is deterministic and reversible. So there is a strong connection between the foundation of thermodynamics and the foundation of the classical mechanics. Another thing that we can understand more clearly is that if our systems are deterministic and reversible, there cannot be attractors or repellers. That is, there can be a stable equilibrium where all the states go to, or an unstable equilibrium, a state where things flow out of. Because if you would have a stable or an unstable region, an attractor or a repeller, the region, the densities around these regions, the areas would shrink and the density would become more and more concentrated. And so this is why I said in other videos before that really Hamiltonian mechanics cannot give you dissipative forces that are not conservative, because you can't have a attractor, you can't have things that the sort of probability distribution that shrinks around in a space. And so this is really a better way to understand why Hamiltonian mechanics can't give you this type of motion. Okay, so we have this characterization now, this physical characterization in terms of reversibility. But we have to be careful when I talk about reversibility in the first sense. I was talking, as I said, about this dynamical reversibility. That is, I can reconstruct the initial state if you gave me the final state. And since we talked about thermodynamics before, it's useful to point out that thermodynamic reversibility is something different. It's either the ability to undo the change, to actually find a process that goes back to where we started, or equivalently, that the entropy, the thermodynamic entropy, does not increase during the process, that it remains the same. And so let's ask ourselves, how does the thermodynamic entropy behave under Hamiltonian evolution? Well, the thermodynamic entropy in classical statistical mechanics is defined as the Kb, the logarithm of the volumes of areas in phase space. Well, we saw before that volume is conserved and the logarithm is bijective function. So if area is unconserved, then the logarithm of the area is conserved, therefore the entropy is conserved. So again, this is yet another characterization. The evolution is deterministic and thermodynamic reversible. The entropy is conserved, gives us conservation of volumes, gives us Hamiltonian mechanics in 1 degree of freedom. Okay, this is one type of entropy. Another entropy that we use is the information entropy, which in this case is the Gibbs entropy, which is basically the Shannon entropy calculated when we're expressing things in canonical variables, in position and momentum. And if you do the calculation, what happens is that the entropy on the original distribution becomes the entropy of the final distribution minus the average of the logarithm of the Jacobian. And if you want to pause and see how the math works, it's essentially what happens is that you have a logarithm of a product which becomes the sum of two things, and the other Jacobian here gets absorbed by the variables, right? So this is a standard result of how the information entropy changes through changes of variables, and therefore also through the evolution from Hamiltonian evolution. And we can really understand how this works because the Jacobian tells us how much we are shrinking or stretching the distribution. So for example, let's assume that we have a distribution here, and this area we are shrinking it down, so the Jacobian is decreasing, and what happens is that the distribution becomes more peaked. And in this area where we are stretching, then the distribution becomes more flat. And where we are peak, we are going to have less entropy, and when we have more uniform distribution, more stretched out distribution, you're going to have a greater entropy. So you can see that depending where you are in the distribution, depending on the Jacobian in that part of the distribution, your entropy is going to go up or go down. But of course, this is the Jacobian, and if we have the Jacobian determinant is 1 everywhere, then the logarithm of 1 is 0, then it means that the information entropy is conserved for all distributions. So saying that the evolution conserves the information entropy is exactly saying that the Jacobian determinant is going to be 1, and for 1 degree of freedom, Hamiltonian is going to give us Hamiltonian mechanics. So yet we have another characterization in terms of information, which also makes sense, because essentially what we're saying is that deterministic and reversible evolution is essentially preserve the information. If I told you exactly what the initial state was, I'm also telling you exactly what the final state is. So if I give you some information about the initial state, I'm going to give you exactly the same amount of information about the final state. And this is also tells you why there is a connection between information theory and physics, because it really tells you how the entropy evolves through time. It tells you whether the system is deterministic and reversible, or how much fails to be deterministic and reversible. So it's an important quantity also in physics. Now, another thing that you might ask is, what about uncertainty? Some people say that information entropy is related to uncertainty, even though the connection is not really quite so tight. But anyway, there is a relationship between uncertainty and information entropy. So what actually happens to uncertainty? Well, we can look at with a measure of uncertainty that is more precise for uncertainty, which is the covariance matrix. And in fact, the determinant of the covariance matrix is something that it's coordinate independent. So you can change coordinates, and if you and the covariance is going to be invariant if you have a distribution that is very, very tight and very packed. And the way that you typically draw the covariance matrix is by drawing these ellipses, and this essentially tells you the standard deviation on one axis and the standard deviation on the other axis, and then you basically see how this evolves. And again, if we have a peak distribution, what happens, a peak distribution meaning that the distribution is packed very, very tight, then the displacement field, you can approximate it with a linear transformation, and the covariance matrix transform linearly in that small region. And so you're looking at the determinant of the covariance matrix, and the covariance matrix will again change by being multiplied on both sides by a Jacobian determinant, and then the determinant of the product is a product of the determinant. So you have the determinant, the Jacobian determinant square has to be equal to 1, but over a continuous transformation you can't have a negative Jacobian. Therefore, you find that if the Jacobian, if and only if the Jacobian is determined, the Jacobian determinant is equal to 1, the covariance matrix is preserved, and therefore the evolution conserves the uncertainty of the peak distribution. So again, this is yet another equivalent characterization of Hamiltonian mechanics. So this again tells us, you can sort of understand how things move in phase space. So if you have an original peak distribution, which you basically can think it as a Gaussian, where that single circle represents 1 unit of standard deviation in all direction. This can sort of rotate around, can stretch, but if it stretches on one side, it has to shrink on the other side, because the length and the area must be the same. The area must be the same, so the length and the width and the angles can change, but the overall uncertainty has to be the same. And this also allows you a little bit to understand the uncertainty principle, that there is also an equivalent for quantum mechanics, for classical mechanics, because if you imagine that you start with a certain distribution, you can stretch it in one side and then you're going to shrink it on the other side, such that the product of the uncertainty remains the same. And then you can also rotate it in phase space, and this rotation on phase space increases the uncertainty on both position and momentum, though really there is a correlation between those two. So if you remove that correlation, you get the area, and you find that the area is conserved. So this idea that classical mechanics, stretches on one side and shrinks on the other is, again, one way to really understand what's happening in the geometry in terms of uncertainty of variables. So, to conclude, we have found that there are 12 equivalent characterizations of Hamiltonian mechanics for a single degree of freedom. And I understand that we saw lots of things one after the other, but this gives you a sense to me that it's important, is that we always think that we have an understanding of classical mechanics, everybody understands classical mechanics, but you see that there is a lot of stuff that I would say that most people don't quite appreciate, right? That there is a lot of elements in classical Hamiltonian mechanics that if you understand that there are these 12 equivalent characterizations, whenever you're looking at a problem, you're going to find an angle that allows you to understand that problem better. So let's go through them quickly, we have Hamilton's equation. We have seen that the rotated displacement field is equal to the gradient of the Hamiltonian. We saw that the displacement field is divergenceless. The Jacobian of the type of evolution is unitary, which also means that the volumes and densities are conserved, because the rules of how the volumes and density conserved, they change in time is through the Jacobian. We saw that the evolution leaves this omega invariant, and this omega is the symplectic form that plays a geometrical role in phase space. The evolution leaves the Poisson brackets invariant, because we saw that there is a relationship between the Poisson brackets and this omega. And then the rotated displacement field is curl-free. And of course, if something is curl-free, then it has to be the gradient of something. So again, there is a tight relationship between these two equations. These are the mathematical, geometrical characterization. Then physically, we saw that the evolution is deterministic and reversible, meaning states are mapped one-to-one because volumes count states. We can also say that the evolution is deterministic and thermodynamically reversible, meaning that the thermodynamic entropy does not increase, it remains the same during the evolution. We can also say the same about the information entropy, it remains the same during the evolution. And also we can say that the evolution conserves the uncertainty for peak distribution. If we have distributions that are very small and tight, when we look at them, the uncertainty, meaning the determinant of the covariance matrix, remains the same. So I hope this gave you a little bit more of an appreciation of what the geometry of the physics of Hamiltonian mechanics is. And these are exactly the type of things that I like to do in my project, really go and look at the theories that we think we understand and really understand them a lot better, such that we have a full mapping on what the physics of those equations are. Because now we can think of those equations not in terms of some math things, but in terms of physical properties that the system have conserved. So if you're interested in these sort of results, you can subscribe to this channel. You can also subscribe to my other channel where I look more at the active research. And again, thank you for the attention and see you next time.